Welcome to the video tutorial Compounds Part 3, the mole. This video tutorial will give us an introduction to both the qualities and the quantities of the concept of a mole in chemistry. Very key concept. Let's get started. Okay, so the mole is the amount of a substance, and some people even think that we should call it the chemical amount, because it's near and dear to a chemist's heart. Why is that? Well, here's the mole. The mole can be as simple as saying 6.02 times 10 to the 23rd items. Atoms, elements, compounds, anything. Atoms or compounds. We'll just stay there. Okay. Now, this definition right here was called Avogadro's number. And it's as simple as that, just a definition. So we could have a mole of anything, a mole of watermelons, a mole of shoes, a mole of hats, but it makes more sense to use it in chemistry with atoms or compounds because they're so tiny. But a mole can also be defined as a specific number of grams of a sample. And when we define a mole this way, we call it the molar mass. All right. Now, when we're thinking about Avogadro's number and the atoms, the number of atoms or the number of compounds, this is more of a theoretical perception. Right? This is where if we're thinking about a chemical formula, right? Chemical formulas, or we're going to work our way up to chemical reactions. You know, there's going to be millions and millions and millions of atoms or compounds, but we're going to think about just one or two at a time. That's what our brain can do. Or solution composition. What exactly is floating around in that solution, right? So these are theoretical ideas that will drive our work, but we can't look at these individual atoms or compounds. We don't have atomic tweezers. So in the lab, we need to look at the molar mass, grams per mole, right? And so this is our experimental, right? When we go into the lab, right? When we go into the lab, we can't take out our atomic tweezers and grab one atom at a time, but we can weigh out grams or milliliters of a sample, right? We can make some measurements. So the important thing is the power of the mole is it links what we've learned about at the atomic level, right? Thinking about the structure of these atoms, right? With carbon or silver, that they have different numbers of protons and neutrons, and so they have different masses, right? So when we look at carbon, we know that the average mass would be 12.01 AMU per atom if we averaged out all the isotopes. The beauty of the mole is that this same value, the numerical value that works in the theory world with individual atoms, the same numerical value, 12.01, is also the number of grams in a mole of carbon. So when we have exactly 6.02 times 10 to the 23rd atoms, we get this beautiful connection here where we get to keep the number the same and we just get to swap out the units. And it works for everybody. So for silver, for example, where we have a different ratio of isotopes, the average atomic mass of one silver atom is 107.87 AMU because it's a much larger atom. So if we wanted to have the same number of silver atoms as carbon atoms, right? If we wanted to have 1 mole of silver atoms, if we wanted to have 6.02 times 10 to the 23rd silver atoms, we would need to weigh out 107.87 grams to have a mole. So I'm going to show you. So let's look at this briefly. Put some paper down, right? So here's our carbon, right? And then here's the silver, right? So as we would expect, so there's 1 mole of carbon here, and then there's 1 mole of silver. So because the silver atoms have more protons and neutrons, they have much greater mass. So both of these samples, what do they have that's the same? They both have 6.02 times 10 to the 23rd atoms. They have the same number of atoms, but there's a different mass present based on the atomic structure. Alrighty. Now let's take this. We'll focus on elements for a little bit longer, and then we'll work our way up to compounds. Alrighty, so here's all of our definitions at the top of the page, right? So here's our Avogadro's number or molar mass, right? So this is Avogadro's number is a defined term. Now this molar mass, right now it's really simple. We just look on the periodic table for the atomic mass of the individual element. Right? When we get to compounds, we'll have to combine the ratio of atoms with the information on the periodic table. But don't worry, we'll get there. Let's just stay with single atoms for the time being, right? So, right, with carbon, 12.01 grams is a mole, right? Versus silver, which has more protons and neutrons, and so it has a much larger mass. Right, 107.87 grams per mole. Alrighty. Now, which sample contains more atoms? So if we have 21 grams of carbon, right, versus 21 grams of silver, okay? So just intuitively, which sample is going to have more atoms? Go ahead and make a prediction. Alrighty. Now let's do some calculations to see how you did. Right? So we know that for every 12 grams, we will have 1 mole of carbon. So if we take 21 divided by 12.01, we have 1.7 moles of carbon. If we have 21 grams of silver, right, because of the larger mass of each silver atom, it takes 107.87 grams to get a mole of silver. So now we can see that if we have 21 grams of silver, we only have 0.19 moles of silver, right? So definitely, right? 1.7 moles, there we go. This is the larger number, right? 1.7 moles of carbon means we have more atoms. But let's say you're not convinced. Let's keep going, right? So first we used the molar mass. We went from grams to moles, and we could compare the moles directly. But let's say I'm really curious. I want to know exactly how many atoms that would be. Right? 1.7 moles of carbon. Each one of the moles would have 6.02 times 10 to the 23rd atoms. So that 1.7 moles would give us 1.0 times 10 to the 24th carbon atoms. Right? Or we'll just say 10 times 10 to the 23rd carbon atoms. And you might wonder why I'm doing this, but I'll show you. Just a sec, right? So we only had 0.19 moles of silver. And the mole definition never changes when we're looking for atoms or compounds. 1 mole of silver, 1 mole of anything is 6.02 times 10 to the 23rd. All right, so we punch that through our calculator and we get 1.1 times 10 to the 23rd silver atoms. Right? So that's why I did this. Right, so we can see that 10, right? The exponents are the same, so 10 is much bigger. So I probably belabored the point a little bit, but I really want to emphasize this. We can compare moles of a substance, or we can compare atoms of a substance chemically. That is chemically sound. Notice we cannot, both samples were 21 grams. So the masses were the same, but chemically they had different amounts of substance. So if we wanted to do reactions, we have a lot more atoms of carbon available than we do silver, right? So the bridge is the mole is this very important bridge that gets us from the individual atoms, and compounds, right, to the lab where we can weigh with grams. Okay, and the cool part is that this bridge happens because it actually takes into account the differences in the atomic structure of the elements forming the compounds of interest. So that is what makes the mole such an important and powerful concept. So we've spent some time getting to know the mole with individual elements. Let's go ahead now and get a little more challenging. Let's look at compounds. All right. So this just adds another layer to it because now we have a chemical formula. So let's look here. Remember that the chemical formula is the fixed ratio of atoms, and now we can take that one step further. We can think about it in terms of the mole ratio, right, of atoms that form 1 mole of the compound. All right? So let's compare calcium chloride with glucose, right? So if we're thinking, we could say, oh, there's 1 calcium ion and 2 chloride ions. But now that we know about the mole, we could say, oh, there's a mole of calcium and 2 moles of chloride. All right, see how we can interchange individual ions with moles. All right, so let's compare these. What type of compounds are these, right? Well, with calcium chloride, right, we recognize that we have a metal, right? And then we have 2 chloride ions, are nonmetals, right? So you have metals and nonmetals, so we know that this is an ionic compound. And then when we look at glucose, right, we see all nonmetals. Okay, and maybe we should draw some notes here, right? So with calcium, we recognize calcium as a metal and chloride as a nonmetal. So whenever we have a mix of metal and nonmetal, we know that we're going to be forming an ionic compound, right, with the loss and gain of electrons. And here with all nonmetals, this is going to be a covalent compound. So here all of the atoms will share. Now, this has a huge effect when we look at the structure of these compounds when we dissolve them in water, right? And we talked about that was another important way to think about the mole, right? Solution composition. So if here we have our salt crystal of calcium chloride and we put it into water, right? We're going to get calcium ions, and then we're going to get 2 chloride ions. Or for each mole of calcium chloride, we'll get 1 mole of calcium ions and 2 moles of chloride ions, right? So we will get that 1:2 ratio, which we see in the chemical formula. On the other hand, when we look at glucose, now the structure is a little tricky, so you're just going to have to just trust me on this. I'm going to show it this way. Pretty soon this will be an old friend, right? But notice the structure of glucose. Look at all of these hydroxyl groups, okay? So I did this in a skeletal line structure. Each corner is a carbon, and we'll talk more about that very soon. But the important thing to notice is look at all of these hydroxyl groups. They love to interact with water, and so glucose likes to dissolve in water, right? But this is an important thing to keep in mind, that for the ionic compound, these become independent ions in solution, right? Where with covalent compounds, the molecules stay intact, right? So formula units separate out, molecules stay together. So a very important distinction, and a good example of how we can look at the mole ratio. Now, let's look at some questions similar to what we did with silver and carbon. Let's say we have 21 gram sample of calcium chloride, right? So if we have 21 grams of calcium chloride, how many moles would we have? Well, we're going to need to determine the molar mass, right? So the molar mass comes from the chemical formula and the periodic table. So for calcium, right, we have 1 calcium, and if we look on the periodic table, that calcium weighs 40.08 grams. And then the chlorides, we have 2 of those, right? So the 1, I'll put the 1 there. Maybe we should put those in red, okay? So the 1 and the 2, those come from the ratio. So 1 calcium, 2 chlorides. The mass comes from the periodic table. So when we add those all together, 110.98 grams per mole. It's very important to put the units. They're going to help you, right? So here we're being asked to calculate the moles, and we're given the grams. So it takes 110.98 grams of calcium chloride to have 1 mole of calcium chloride. So we can cancel out the grams, and we're left with moles. Punch this into our calculator, and we see that we get, that's an inch, right? 0.19 moles of calcium chloride. Okay, now let's try glucose, right? As we could start to suspect, right? Ask yourself right now, do we expect there to be more moles of glucose or less? It's a much bigger molecule, has a lot more atoms. They don't necessarily weigh as much, but there's a lot more of them. Well, let's double check, right? Carbon, we'll keep going with the color coding, right? So there's 6 carbon atoms, there's 12 hydrogens, and there's 6 oxygens. So these numbers in red came from our mole ratio. Then we look on the periodic table, and we get the molar mass for each element, right? And we add those all together. Glucose weighs 180.18 grams per mole. Now that we have the molar mass, we can say if we have 21 grams, and glucose, we'll just give that a big G, right? So it takes 180 grams of glucose to make 1 mole of glucose. So we can see here that 21 grams is only going to be 0.12 moles of glucose. All right, so it seems a bit counterintuitive, right? But if we think about it a little deeper, it starts to make sense. If the molar mass is smaller, it takes less grams to make a mole, so we end up with more substance. If our sample is heavier, if it has a larger molar mass, it takes a bigger sample to have the same number of compounds, of molecules. Alrighty, so let's just do a couple more questions to wrap this up for this page, right? How many moles of chloride ions are present in that 21 grams? Okay, so we'll keep going, right? So the 21 grams gave us 0.19 moles of calcium chloride. So how many moles of chloride ions, right? So for every mole of calcium chloride, we would have 2 moles of chloride ions, right? That's what the chemical formula tells us. It gives us the mole ratio. So we would have 0.38 moles of chloride ions. And similarly, right, now we have 21 grams of glucose, so right, glucose has a higher molar mass, so we ended up with less moles. So if we have 0.12 moles of glucose, if we look at the chemical formula for glucose, we would say that for every mole of glucose, right, how many moles of carbon? Right, very straightforward, right there, right? We would have 6 moles of carbon atoms. Okay, so once again, right, see, like moles are canceling, and then we're left here. Okay, so we plug that in our calculator, 0.72 moles of carbon atoms. Alrighty, so we want to be comfortable using the molar mass to go from grams of a substance to moles of a substance. And we want to recognize that the chemical formulas are also mole ratios when we think about having a mole of the substance. Okay, and now let's take this one step further. Let's look at chemical reactions. Okay, so we've talked about all the different ways that the mole is important. So let's do a grand finale here. All right. Molecules and moles can be used interchangeably because they're linked by Avogadro's number. So I think that's why chemists love them so much. All right. Atoms or molecules. Okay. So as we can see from those previous examples, right, we can't compare grams of samples directly. We have to adjust for the different atomic masses of the elements involved, right? Because different elements have different numbers of protons and neutrons. All right, so everything links back to that basic atomic structure. Pretty cool. All right, so here's our buddy glucose, right? Glucose can react with oxygen to produce carbon dioxide and water. And this is a balanced reaction, so let's look at what that means. Well, in terms of the number of molecules, is it balanced? Well, we have 1 molecule of glucose reacting with 6 molecules of oxygen, right, to make 6 molecules of CO2 and water. Well, that doesn't look balanced. Let's try moles, right? We could say 1 mole of glucose reacts with 6 moles of oxygen to produce 6 moles of CO2 and 6 moles of water. All right, let's dig in a little deeper. Let's look at the molar mass. Okay, so we've already done the molar mass for glucose on the previous page. It's 180.18 grams per mole. Oxygen's pretty simple, right? 2 times 16, so 32 grams per mole. Carbon dioxide, right? 1 carbon and 2 oxygens. All right, so 44.01 grams per mole. And water, all right? 2 hydrogens and 1 oxygen. Okay. Alrighty, so now let's see. Why do we say that this is a balanced reaction? Well, let's look at the grams from the mole ratios, right? So if we have 1 mole of glucose, and that would be the 180.18 grams. But we have 6 moles of oxygen, and they each weigh 32, right? So if we have 6 moles, 32 grams per mole, right? So then that gives us 192 grams. Okay, CO2, right? Once again, we'll do the same thing. We have 6 moles and they each weigh 44. So that's going to give us, I'm not going to show you how to do the calculation because we just did it, right? And then we have 6 moles of water, right? So each mole weighs 18.02. So if we have 6 moles, we would have 108.12 grams. Now let's look, right? If we add this all up, 372.18 grams is the reactants, and 372.18 grams is the product. So we can see that overall, the balanced reaction does obey the conservation of mass. We have the same amount of mass. And we could also look at this just in terms of atoms, right? Carbon, hydrogen, and oxygen, right? If we look on the left, we see only 6 carbon atoms. And when we look on the right, our product has 6 carbon atoms. Hydrogen, there are 12 hydrogen atoms on the right as a reactant, and 12 hydrogen atoms. So that was on the left. There's the right, 12 and 12. And then oxygens, right? 6 and 12. So 6 plus 12 is 18. And here we have 12 plus 6 is 18. So we see that the mole is the aspect that helps us create balance and follow the conservation of mass. Alrighty, so that wraps up this tutorial introducing you to the important concept of the mole. Please spend some time and work a few calculations to reinforce your understanding of this important idea.